Hello. In this webinar we are going to present an overview of work done by the KIOS Research and Innovation Center of Excellence during the Caramel H 2020 project. The presentation will highlight the deep learning approach referred to as DriveGuard, which aims to provide a solution towards detecting and mitigating cyberattacks on the camera sensors of autonomous vehicles. Autonomous vehicles increasingly rely on cameras to provide the input for perception and scene understanding for object detection in 2D and 3D, segmentation, pseudo-lidar, as well as for multimodal systems that combine the inputs of different sensors to achieve inferences on the scene. Hence, the ability of scene understanding models to classify their environment and objects, under adverse conditions and image noise is crucial. Such adverse conditions can be due to weather, physical damage or even malicious data manipulation. This works as an attempt to provide a detection and mitigation solution for the latter. Over the last years it was demonstrated that deep learning-based solutions are susceptible to various threats and vulnerabilities that can cause the autonomous vehicles to misbehave in unexpected and potentially dangerous ways. Recent state-of-the-art models are trained to overcome environmental variations, however the model is still susceptible to physical distortions such as sensor damage and extenuating circumstances. Besides physical attacks that can induce erroneous behavior, there is also the possibility that the camera data can be manipulated directly, thus eliciting false algorithmic inferences. This can cause an AI-based perception module like semantic segmentation to erroneous inferences, making the controller take incorrect decisions, such as when an autonomous vehicle fails to detect a lane parking marking, which can result in a collision. Crafting appropriate defenses against attacks at the sensor signal layer is important for realizing autonomous driving. Traditional techniques have utilized signal processing and filtering to remove noise under some modeling assumptions. However, more elaborate image deterioration attacks can add artifacts in the scene and hence cannot be addressed with traditional techniques. For this reason, deep learning solutions based on autoencoder structure have been proposed to reconstruct perturbed images. We build on this approach and improve it by adding skip connections and spatio-temporal information to the model. The main work that was carried out was on the development of the DriveGuard model, a lightweight spatio-temporal convolutional autoencoder model as an image reconstruction tool for robustifying perception tasks such as semantic segmentation for autonomous vehicles. The work involved investigating different loss functions and architectures to derive the best model. Finally, we constructed a more challenging dataset and utilized an autonomous driving simulator to evaluate the solution on a real embedded platform. First, we are going to highlight the development of the model. Rather than having to retrain a segmentation model with noisy input, we instead investigate a more universal approach, referred to as DriveGuard, that first passes the camera image through a convolutional autoencoder that learns to restore the image quality and robustify the image segmentation process. At a high level, the model receives a sequence of images and aims to retain the image quality by mitigating any distortions. Notice that when the segmentation model receives the attacked image, the damage can be quite high. But when the image is reconstructed by DriveGuard, it is possible to identify main objects of interest. The first step towards developing the model is using an appropriate dataset. We chose the Cityscapes dataset, which has ground truth high-resolution segmentation annotations. In addition, we also construct a diverse dataset using the Carla autonomous vehicle simulator. In this way we can train the model with a synthetic dataset able to capture various weather conditions as well as realistic driving scenes. Diverse weather conditions include rain, cloudy, as well as sunset and night. In this way the model will also be robust to environmental conditions. The synthetic dataset was used for both the training and testing of both the autoencoder as well as a DeepLab v3 segmentation model. The model is then trained by stochastically generating an attacked version of an image and then using the original image as the target output. To further improve the model performance, we probabilistically apply augmentations such as cropping, rotation and color change. The model must then reconstruct the original image and remove the effect of the attack. In case that the input image is not attacked, it is expected that the model will retain the image information. The overall reconstruction error is used as the loss signal. We implement the model in both TensorFlow and PyTorch and was trained for 200 epochs. Let's look now at a bit more detail at what types of attacks we have considered. First, we consider classical noise types such as Gaussian noise, speckle noise and salt and pepper with random variance. Beyond that, we also investigated more attacks that add specific structures and artifacts to the image. That is the addition of lines which can be due to stacked pixel values, and blank regions that hide parts of the image. These are applied in random locations in the image with varying degree. Now let's look at the architecture in a bit more detail. First, the architecture employs separable convolutions instead of classical ones in order to reduce the number of parameters and also make the computation more efficient. It follows an encoder-decoder structure where the encoder downsamples the image and tries to capture high-level semantics, and the decoder uses the semantic information to upscale an image and remove the effect of the attack. We develop different versions to evaluate the impact of different design choices. First, a traditional convolutional autoencoder is developed. Then skip connections are added where features from the encoder are propagated to the decoder to enhance it with low-level information. And finally, we incorporate temporal information by feeding the model with features extracted from the previous frame. This final addition permits the model to reason holistically about a scene and better restore missing content. To train the different autoencoder architectures, we explore two loss functions which we apply as standalone and combination to study their influence. Specifically, we adopt the mean square error, which is typically used to directly regress pixel values, and the structural similarity index measure, which can be used to assess the structural similarity between two images. We choose these among the plethora of existing indexes, because they are established measures, and because they are differentiable, which is requirement for the backpropagation stage. To evaluate the effectiveness of the developed architectures to mitigate attacks on the image and subsequent segmentation map, we employ the DeepLab V3 model. To evaluate the segmentation output, we utilize segmentation metrics such as the per-pixel class accuracy and the IOU score. Furthermore, we also use the peak signal-to-noise ratio to evaluate the reconstruction performance of each autoencoder model. To draw inferences on the impact of noise level on the segmentation and reconstruction performance, we parameterize the amount, variance and number of artifacts and construct 5 different noise levels for each type of attack. In terms of quantitative results, the simple autoencoder trained using the MSE loss can effectively reduce noise and make the scene perception model more robust, as it achieved to double the semantic segmentation metrics on attacked images. However, this simple autoencoder had comparable quantitative results with the traditional approaches such as the median and bilateral filters. In terms of the comparison between the autoencoders, the refined autoencoder with skip connections is significantly stronger against all the different noise levels compared to the plain autoencoder and the traditional approaches. When evaluated using the traditional metrics, it manages to have 30% better mean square error and better structure similarity by about 4.5% than the plain autoencoder. Of equal importance is the impact of loss functions. There is a clear trade-off between the two loss function where the pixel-wise MSE learns to mitigate small details, whereas the regional SSIM is a more robust approach for the stronger attacks. These observations solidify our earlier intuitions on the matter, that the perception engine's evaluation trends are not analogous to the mitigation trends of the pixel-wise metrics. In contrast, SSIM has a more analogous relationship with the perceptions engine's performance. Thus, the choice of SSIM as a loss function seems more appropriate in order to train an autoencoder which can make the perception process more robust. Based on the results, it is evident that the sequence-based spatio-temporal autoencoder outperforms the simpler models under every evaluation metric across all noise levels. Interestingly, the model outperforms in traditional metrics even the models that use the equivalent metric as their loss function. In respect to the patch-level metric SSIM, the results prove that the model can appropriately align features from sequences of frames and handles shifts in motion. The effective accumulation of features from the different frames is evident by the pixel-wise metrics PSNR and MSE. In terms of the perception engine evaluation, the spatio-temporal autoencoder significantly outperforms the rest of the autoencoders. The most interesting observation, however, is that the model manages to reach pixel accuracy equivalent to the unguarded image when faced with a non-attacked image, at 74.9%. Moreover, it keeps its performance above 70% for attacks which are not extreme, and above 60% when the noise is extreme. Let's see now some qualitative results. As we can see in the figure, when an image is attacked with blank regions, the spatio-temporal autoencoder can restore sections of the image that are obscured by this attack. In essence, this is possible because part of that region might have been visible in the previous frame. Something that the plain autoencoders simply cannot do even if this was part of the training phase. The results are extremely promising as they establish the model's robustness against attacks that involve selective occlusion of important features in the frame such as road lines. As shown in the video results for synthetic data, the proposed spatio-temporal approach manages to improve the segmentation output. This is particularly important since even with mild attacks the segmentation map can be completely destroyed without the use of DriveGuard. We also see similar results in the Cityscapes dataset with real video sequences. With the use of DriveGuard, the adverse effects are mitigated. As a result, important elements such as other vehicles, pedestrians and drivable area are correctly identified. What we have seen this far is an approach where the input image is passed through the DriveGuard model and the output image is passed to the segmentation model. This is a passive process that does not detect if an attack has actually taken place. We can take advantage of the observation that when the input and output of the autoencoder are almost identical, it means that the autoencoder did not have to make changes to the input. So we can assume that the input is not attacked. All other cases can potentially signal either that an attack has taken place or that the autoencoder cannot reconstruct the image, thus it might be an out-of-distribution sample. Thus we can design a detector by looking at how similar the input and output of the decoder are. We have experimented with different types of detectors. From a simple one that applies a threshold on the reconstruction error to more elaborate approaches where we integrate the detection part into the learning, either through an additional neuron using the bottleneck, or an additional network that takes as input the two images, or by applying machine learning algorithms on top of extracted similarity measures. All approaches gave good results. This now completes our solution for a holistic detection and mitigation approach. Let's see how we managed to deploy it using a hardware-in-the-loop approach. This is the deployment and testing architecture. It is comprised of three main parts. On one end we have the simulator or data generator. For the purposes of our solution, we used the Carla simulator to act as the autonomous vehicle. This was done for practical reasons, but it could also be real data coming from a real autonomous vehicle. This is possible because we use the ROS framework to interface with the outside world. We will talk more about it on the next few slides. Moving on, we have the anti-hacking platform. It is essentially an embedded device, in our case an NVIDIA Jetson platform, that runs the DriveGuard model to detect and mitigate attacks. We implement the model to run on the GPU of the embedded device, thus enabling the processing of over 10 frames per second. The last part of the deployment solution is the visualization, where we show the results with, and without the proposed solution, to demonstrate the impact of the attack. As already mentioned, we use the ROS framework for communication between the anti-hacking device and the outside world. This is important because ROS provides a universal way of integrating the solution in various ways. For instance, we have a version that runs on a server. As such, the solution can act as an on-demand service to any autonomous vehicle that needs to verify its sensors. This slide provides some more details on how we implemented the different components using ROS. Even for the case of an attacker, we simulated it as interfering with the ROS node and altering the image signal. This is a realistic assumption given that a malicious actor can gain access to the internal system of an autonomous vehicle and interfere with the sensor data. DriveGuard also has access to the same camera sensor information and is able to act through its detection and mitigation process. Now we will see a real demo of the system running on a Jetson NX while interfacing with a PC running Carla to receive images through ROS. As we can see, the top right image has all the noise removed, and as a result its corresponding segmentation map on the bottom right is directly usable for scene understanding tasks. While on the left both the attacked image and the segmentation map are negatively impacted by the attack. If you would like to find out some more details on the proposed solution, you can have a look at the following publications that detail different aspects of the proposed solution. The Caramel project deals with different cybersecurity aspects of connected and autonomous vehicles. So, there are many more activities that have taken place in parallel to what was presented here. Please have a look at the various social media channels and the official website of the project for more information. Thank you for your time.